Alright, we're going to go ahead and start the lecture. It's going to be a new lecture, so make sure you have received this packet. So say 4.5 exponential and logarithmic models on top. So make sure everyone's got this packet out and we're ready to take notes. And you'll want your calculator for this lecture, so I recommend you pull that out as well. Feel free to pause the video if you need to get these things. But we can use the skills we learned in solving exponential and logarithmic equations to solve real-world examples represented by said exponential or logarithmic models. So two common formulas that you've seen before in finance are compound interest. So if you need a little refresher, compound interest formula looks like this. And then the continuous compound interest formula looks like this. So I'll give you guys a moment to go ahead and write those down. So while you write those down, A stands for the amount in the account, P is the principal, R is the rate, N is the frequency of compounding, T is time. So Taylor has, let's look at this first example. Taylor has $3,500 to invest. She finds a bank offering 5.25% compounded quarterly. How long until the balance reaches $4,000? So since it's compounded quarterly, that tells us to use the compound interest formula. So we're going to take our compound interest formula right here, and we're going to set the amount to 4,000. So we're going to plug in 4,000 for the amount. And then the principal is $3,500. That's the amount put into the account. And then let's keep punching the numbers in the formula. We got 1 plus R stands for the rate. So the rate is 0.0525%. And then the N stands for frequency of compounding. So quarterly means 4 times per year. And that's raised to the 4t. Because we don't know how much time it is. Alright, so first things first, I want to go ahead and divide both sides by 3,500 and start isolating this exponential. And like I said, this is that'll cancel out the multiplication right there. So division cancels out multiplication. So this is where the calculator is going to be useful. Switch that to a fraction. So that's going to be 8/7. And then I'm going to go ahead and type this base in. So 1 plus the quantity 0.0525 over 4. So that'll simplify that. We're going to go ahead and round that to 4 decimal places. So 1.0131 roughly raised to the 4t. Now note that this is an exponential equation. We know it's exponential because the unknown value is in the exponent's place. So we talked about solving exponential equations 2 lectures ago. And the way we want to solve this is by using logarithms on both sides. So we're going to go ahead and log both sides. We're going to log the left and log the right. If you recall, properties of logarithms let us pull that exponent out front. Give you guys a moment to write that down. So we use logarithms on both sides, and properties of logarithms let us pull that exponent out front as a coefficient. And now all we got to do is divide. So to undo multiplication by 4, I'm going to divide by 4 on both sides. And then to undo multiplication by the logarithm of 1.0131, I'm going to divide by that on both sides. Alright, and those will cancel. And we can go ahead and just type this into the calculator. So we have natural log of 8/7 divided by the quantity 4 times natural log of 1.0131. As you can see there. And that's roughly 2.56 years. So it'll take roughly 2.56 years to reach that amount. So this is just plugging numbers into a formula and using those solving skills we learned from 2 lectures ago. Let's go and look at another example. ABC Bank is offering to double your money. They say that if you invest with them at 6% interest compounded monthly, they will double your money. If you invest $1,500 in the account, how long will it take to double your money? So, at 6% compounding monthly, so again, we're going to use that compound interest formula. I'll go ahead and rewrite it down here. There's that compound interest formula. A is the amount or balance, P is the principal, R is the rate, N is frequency of compounding, T is time. So, we want to invest $1,500. That's the principal. The rate is at 6%, 0.06. It's compounding monthly, so it's 12 times per year. We don't know how much time it's going to take. It says how long will it take, so we don't know T. We want to know how long it will take to double. So if we put in $1,500, it will have doubled when the amount reaches $3,000. That's when it will hit double, and then solve the equation. And honestly, solving all these compound interest exponential equations is always going to be the same steps. Divide, log both sides, pull the power down, wrap it up. It's always the same steps. We're going to go ahead and divide. Those cancel, so that equals 2. I'm going to go ahead and simplify the base of this exponent. So I have 1 plus 0.06 over 12, which is 1.005. Raised to the 12t. And then I'm going to go ahead and log both sides. Maybe I'll use a capital N to make it a little easier to read. Log the right. What you do to one side, you have to do to the other. So I'm going to log both sides. The whole reason we do that logarithm is because it lets us pull the exponent down. That's why we do it. So the whole reason we do it is so that we can pull that exponent down front as a coefficient. Right? So we can take that and pull it out front. And then just divide. So to get rid of times 12, we'll go ahead and divide both sides by 12. And to get rid of times natural log of 1.005, we'll divide accordingly. What you do to one side, you have to do the other. And those will cancel there, so now t is by itself. So all we got to do is punch it in the calculator. So we got natural log of 2 divided by the quantity, 12 times natural log of 1.005. So it'll be 11.58. So it would take just shy of 12 years for your money to double at that interest rate and compounding monthly. So you can see step for step, these two examples are about the same. Let's go ahead and look at the next example, flipping on over. Maggie wants to have a total of $8,000 in 2 years so that she can put a hot tub on her deck. She has $5,500 to invest. She finds an account that pays interest compounding continuously. How much interest will the account need to earn so that she'll have $8,000 at the end of 2 years. Alright, so if we want to take a look at this, so we take a look at this one, we're going to need that compounding continuously formula. So I'll write right here. So we want the amount to equal $8,000. And we're going to invest $5,500. We don't know what R is, but we know T is 2. We want it to take 2 years. And go ahead and solve the equation. So basically, all you got to do is isolate it, log both sides. So all the steps from the previous problems are the same. Basically, first step is divide. So 8,000 divided by 5,500 is going to be 1.45. We'll go round it to 2 decimal places. E to the 2r, just bringing that down. And then we're going to go ahead and log both sides. So to solve that exponential equation, just log both sides. Log the left, log the right. The whole reason we apply that logarithm, again, just like the previous 2 examples in previous lectures, is so that we can pull that exponent out front, where we can manipulate it. So that lets me pull it out front. And remember, from previous lecture, natural log of e just equals 1. You can even verify it on your calculator. So you see natural log of e equals 1. So if I bring all that down, all I have to do to get r by itself is just divide by 2. And there's my answer. So let's go ahead and punch that in. So natural log of 1.45 divided by 2. And it's going to write that as a percentage. So that's going to be roughly 18.58% is what interest rate would be required. So pretty high interest rate to accomplish that goal. Let's go to look at number 2. Peyton plans to put her graduation money into an account and leave it there. She receives $750 in graduation money that she puts into an account. There is 4.25% interest compounded semi-annually. How many years until Peyton triples her initial investment? So this is going to be compound interest. I'll write the formula here. Same formula we used on the first 2 problems. Start plugging in the numbers we know. So we're going to invest $750. The interest rate is 4.25%. 0.0425. It's compounding semi-annually. Semi-annually means twice per year. We don't know how much time it will take, but we want to triple it. So we want to triple the 750, which would be $2,250. That's when the account will have tripled. So just multiply by 3. And then solving this is going to be the same exact procedure as solving the other examples. Same exact steps. We're going to go ahead and divide. Just like that. Oh, hello. And then that will get us 3. And then we can go ahead and simplify that base. We can go ahead and simplify the base of that exponent. So that's 1 plus 0.0425 divided by 2. And we'll go ahead and write that down. So that's 1.02125. All raised to the 2t. So what we're going to go ahead and do is we're going to go ahead and log both sides. Same exact step as all the other problems. That lets us pull the power out front. So we have natural log of 3 equals 2t natural log of 1.02125, and then just divide and done. So perhaps you're noticing the pattern here. And we'll just punch that in the calculator. So we got natural log of 3 divided by the quantity. In your denominator, make sure you got it in parentheses. 2 times natural log of 1.02125. And that's going to get me that value, 26.12 years. Alright, so let's flip on over to the next example. So this was a little more straightforward. The equation is provided, so we don't have to solve anything. Determine the population after 22 years, just plug in 22 for t. So if we know the time value, nothing needs to be solved, so just type it in. So all we got to do is plug in the 22, and we have the answer. That's because p is already by itself. So the population is already isolated and defined. We'll round that to the nearest fruit fly. Or dolphins, I'm sorry, this is dolphins. Round to the nearest dolphin, so roughly 116,000 dolphins. Closer to 117,000, truth be told. Question is, when will the population reach 50,000? Now this is going to require more effort. So we're going to set the population equal to 50,000 and solve the equation. So plug in 50,000 for the population. Note that this is an exponential equation, so solving it's going to be the same as all the other ones. We're going to isolate it, then log both sides and go from there. So divide both sides by 25,000 to isolate that exponential. So that means we're going to have 2 equals e to the 0.07t. Once it's isolated, let's you write that down. We're going to go ahead and log both sides. And then remember, the whole point of that logarithm is so that we can pull that power out front as a coefficient. Alright. And we're basically done. There's our answer. Remember, natural log of e just equals 1, so you can ignore it. So solving these natural exponential equations is actually a little bit easier. So let's see what we get. Natural log of 2 divided by 0.07, roughly 9.9 years. Is the answer. All right. So let's go ahead and look at example 6. And then 7, so last two examples. A city's population is growing at a certain rate r. After t years, the population is given by this equation, or this function. Find the rate of growth if the population reaches 1,001,493 after 10 years. So what we're going to do is plug in these values and solve for r. So p at t represents the population at time t. So we're going to set the population equal to that number. All right. And that's going to equal 450,000 times e. We don't know what r is, but we know what t is. T is, we're setting it to 10. 10r. And then you solve this equation the same as the others. Go ahead and divide. Let's write that down for a moment. Let me me go ahead and use that calculator here. So, 1,493,000 divided by 450,000. Now we'll go to round that to 2 decimal places. That's roughly 2.23 equals e to the 10r. So once you've isolated it, as you can see here, just go ahead and log both sides. So if you go back and look at all these problems, you can realize it's the same exact steps for every single equation. Isolate it, log both sides, pull the power down, wrap it up. So if I it's going to pull that power down out front. All right. Remember, natural log of e just equals 1, so you can just ignore it. So all I'd have to do is divide by 10 to finish solving. So I'll punch that into the calculator. And the rate is roughly, if I write that as a percentage, 8.02% would be the answer. All right. So just to summarize this example, just plug in the population, plug in the time, solve for the unknown value. This problem is going to be no different, except now we're plugging in a number for r and a number for the population, and we're solving for t. But the steps are going to be the same. So plug that number in for the population. And then set r to 3.5%, which is 0.035. And this time t we don't know. If it's asking for when, that means we don't know what t is. And solve the equation. And again, solving this is going to be identical to all the previous examples. You're going to divide, log both sides, pull the power down, wrap it up from there. Let's go ahead and divide. So this is where we'll use the calculator. Now we'll round that to 2 decimal places, so roughly 1.75 equals e to the 0.035t. So let you all write that down. And now time for the key step. We're going to go ahead and log both sides. And then that lets you pull the power out front. Remember, natural log of e just equals 1, so you can pretty much just ignore that and then just divide by 0.035. And that will get t by itself. So roughly 15.99 years. That's how long it would take. So I know we were solving for time in this problem and rate in that problem. The steps were identical. Pretty much divide, log both sides, go from there. All right, last example. Population of fruit flies can be given by that equation with t representing time in days. How many days until the population reaches 100? So, same song and dance here. Plug in 100. All right. Then same sequence of steps. We'll go ahead and divide. 100 divided by 33. Let's round it to 2 decimals. That's roughly 3.03. And then to finish solving, we're going to go ahead and log both sides. Log the right, log the left. Whole purpose of logging both sides is so that we can take that exponent, pull it out front. So I can pull that entire exponent out front as a coefficient, and we're pretty much at the end. Remember, a natural log of e just equals 1. 1 times anything is itself, so we can ignore that. And then just divide. And we're done. And we get roughly 20.16 years. If we go ahead and round it to 2 decimal places. Or not years, days. Units in days. And B, honestly, B is the same exact problem. The only difference is you swap the 100 out with a 200. So I'll go ahead and omit that problem in the interest of time. It's identical, essentially. There's nothing different about it besides the number. So I want you guys to go ahead and start working on that homework. That homework assignment is actually going to be due at the end of class. So I want you guys to finish that homework assignment before the end of class, so that way you don't have any homework over spring break. On that note, have a wonderful day, and just shoot me an email if you have any questions.